Good morning, dear colleagues. Thanks to the organizer for inviting me and for giving me the opportunity to talk about edge distributed intelligence in the Internet of Autonomous Systems at this year's HiPEAC conference in Budapest, Hungary. The next wave of IoT devices is advancing the technology convergence with the integration of various computing concepts and paradigms, embedded artificial intelligence, hyperconnectivity, digital twins, and expansion into virtual environments. New concepts such as autonomous mesh intelligence IoT, Internet of Things senses, Internet of Autonomous Systems, artificial intelligence of things, Internet of Intelligence things are evolving and develop into enabling technologies for the green and digital twin transition in different industrial sectors. The developments in hyperconnecting technologies bring new challenges, and several issues must be addressed, such as decentralized and distributed computing and the network paradigms, scale of the systems, heterogeneity, device dynamic changes, intelligence connectivity that now combines AI, IoT, and wireless cellular communication protocols, device trigger communication, context awareness and self-X capabilities, scalability, efficiency, adaptability, dependability, and transparency of these systems. Internet of Intelligent Things technologies are evolving. We witness the developments of wired network devices, wireless sensor networks, and Internet of Things platforms developments. Now, we are entering a new wave of technology developments addressing the autonomous mesh intelligence IoT characterized by everything intelligent everywhere. New types of IoT technologies are emerging, such as Internet of Things senses, that complements and extends the capabilities of IoT applications by including other senses. For example, vision, hearing, touch, taste, smell, pain, temperature, and providing new perception and experiences by integrating augmented intelligence and information across senses, time, and space. The Internet of Things senses brings as well new challenges such as the development of haptic edge sensor actuators, surface sensing and actuators, multimodal sensory and information fusion, stability of haptic control, ultra-high reliability, ultra-low latency connectivity. In addition, these technologies, these new IoT technologies, accelerate the development of other technologies as metaverse. Metaverse is a term formed by combining meta and universe and has been introduced as a shared virtual world that is fueled by many engineering technologies such as virtual reality and AI. AI has shown the greatest importance of processing large amounts of data to enhance immersive experience and enable human-like intelligence of virtual agents. IoT, intelligent connectivity, distributed ledger technologies, digital twins, machine learning algorithms, deep learning architectures, and swarm intelligence have had a role in the foundation and development of the metaverse, employing augmented reality, virtual reality, and mixed reality. These are now ready to be employed in different industrial applications in the next years. Many challenges have to address as well related to the development of digital twins. As a digital or virtual representation of an IoT physical device, object or system, which are evolving towards modeling and simulation future intelligent autonomous systems of things. As we see, the evolution comes from different areas of the technology and includes the integration, the understanding and learning, predicting and optimizing, automating, and at the end, including of artificial intelligence in these new IoT digital twins. Many challenges have to be addressed related to IoT digital twins. Among these are the aggregation of models in a distributed layered architecture, IoT digital twin precision to duplicate the IoT physical object abstraction computing capabilities, simulation and modeling of the communication channels and influence of the environments on the communication parameters of the IoT digital twins, virtual sensing functions and simulation of IoT digital twins, and as well the work on IoT digital twins counterfeiting, identification, and mitigation. The implementation of new features and functions needed by the new wave of IoT devices require a paradigm shift in the process architecture and computing paradigms, which further accelerate the transition from centralized to decentralized and distributed architectures and computing concepts. This will further strengthen the process of technology convergence and the move to edge distributed solutions and the change of the processing patterns across the computing continuum. The slide illustrates the transition with the centralized decentralized solution presented on the left, middle, and the right side of the slide. And we see that the distributed IoT model is evolving and will be integrated in many embedded AI applications in the future. A distributed system is a collection of separate and independent software, hardware, and communication components called unit nodes. For example, IoT devices, processing units, computers that are networked and work together coherently by coordinating and communicating through messages or events to fulfill and solve a problem together. Several conditions need to be valid for a system to be called distributed instead of centralized or parallel. First, there is no shared clock. The processing units or nodes have their own timers to have their own notion of time to determine the order between events and regulate the time and speed of the processing operations. Each node in the distributed system has its own processor, and balance is achieved through coordination and synchronization. The nodes in the distributed system have no shared memory. Each process has its own independent memory, and the state is distributed throughout the system. Concurrency is another critical characteristic of distributed systems, which means that software and hardware components of the system and the processes are autonomous and execute tasks concurrently. Heterogeneity and loose coupling are essential, meaning the processors are independent, separate from each other, and have different speeds. Several concepts are defined for distributed systems. Nodes in distributed systems run different operating systems, and components can be built with different technologies and run on different platforms. Distributed systems are dynamic systems using overlay networks and allow computing units or nodes to join and leave at will. The overlay networks can be virtual networks built on underlying network infrastructure. Blockchain, for example, is an overlay network on top of the internet. And blockchain, as we know, has a distributed architecture. Distributed computing is a type of computing used for distributed systems. It is concerned with building and establishing computing models for distributed systems and working out algorithms to solve problems related to such systems. Edge and swarm computing are examples of distributed computing. The node unit, for example, again, IoT device, robotic things, a computing processing server, an autonomous vehicle, if we consider an autonomous vehicle application, is an essential part of the distributed system. The node is the software, hardware, and communication component with its own processor and memory and can communicate with the rest of the system. Nodes form groups, a network of nodes that can be joined by the other nodes and devices. The groups are open or closed, restricted in terms of membership upon the type and resources accessibility, and forming different types and intranets. Resources are assets in the distributed systems that could be accessed remotely by nodes in the network or user in the distributed application that turn over the distributed system. The dispersion of resources, the failure of nodes and the failovers, migration and the replication operation, etc., are invisible to distributed system users. This is achieved through components such as middleware, a distributed system layer that connects the nodes together and makes them appear as one single processing system. It is a logical layer on top of the whole distributed system, like a meta operating system, as we know, that runs over the nodes collectively. Once this layer is established, distributed application could be built and run over it. This middleware layer manages resources, provides communication and security services, and handles failures and the other complexity of distributed computing. Concurrency is an intrinsic property of distributed systems, since multiple operations and activities are executed, and these activities interact with each other to perform a particular operation. Coordination and synchronization are concepts that manage the issues of shared clock between processes and solve data corruption and inconsistency problems. In autonomous distributed system, the architecture model is essential for the hardware, software, and communication components, as it defines how the nodes in the system are organized. It distributes the network structure and how nodes communicate and interact while enhancing system management and maintenance. The overall states of the distributed system are the union of the states of the separate processes and are offering a global view of the system that describes its properties at a particular point in time. The Internet of Autonomous Systems are conceptually built as distributed systems that allow for resource sharing, scalability, availability, reliability, and reaching consensus for optimized solutions. The implementation of distributed autonomous systems in terms of scale uses different types of distributed computing, cluster computing, and grid computing, for example. While in cluster computing, distributed computing systems, the underlying infrastructure is composed of identical nodes that are closely connected. Distributed grid computing is a type of system in which heterogeneity of nodes is the benchmark in terms of hardware, software, and technology. Different architectural styles are applied to distributed systems, such as layered architecture, where nodes are grouped into separate layers, each with each specific goal to achieve. An example of a layered distributed system is the client-server model, for example. Object-based architecture, where nodes are less structured and loosely coupled than the layered model. Communication is synchronized, and the system's elements and nodes can directly interact with other nodes through a direct exchange. Another architecture model is the data-centered architecture, where the nodes are designed to communicate through a shared repository. The system uses a data center through which primary communication happens. The events-driven architecture reaches their goal by employing events. Nodes communicate and perform operation through the propagation of and the reaction to events. What are the advantages of distributed system? Why we are focusing so on the new paradigm of implementing distributed systems for the autonomous IoT solutions? One, it's reliability. The other, it's scalability. The other, it's tolerance. However, failure detection is challenging in distributed systems, considering large systems that evolve over time. Design for failure must be considered in distributed systems with the assumption that the network is not reliable and secure, that the topology of the underlying network is changing, or the latency is not zero. In designing and implementing Internet of Intelligent Things, several concepts and computing paradigms are used in order to implement these systems. Such concepts are edge computing, that we are discussing today, ubiquitous computing, neuromorphic computing, and swarm intelligence. All these paradigms and concepts are used in order to address the 6 A's and the C's used by IoT systems. The A's are anyone, anything, anytime, anywhere, using any path and any service. And for the C's, the IoT devices are used to collect, connect, cache, compute, cognize, and create new value from the data processed. The terms that we are and the concepts that we are naming here are defined as, for example, for edge computing, a concept and the distributed computing paradigm that brings processing and computation and data storage closer to the sources of data. This is done to improve response time and reduce communication bandwidth. Edge computing is in a way an architectural topology and location-sensitive form of distributed computing, which is a field of computer science that addresses distributed systems. On the other side, ubiquitous computing is a concept in software, hardware engineering, and computer science where computing is made to appear anytime and anywhere using any device in any location and in any format. In a way, it's a representation of what are some of the goals of IoT applications. The paradigm is described as well as pervasive computing ambient intelligence or everywhere, with each term emphasizing slightly different aspects of the concepts. If we are focusing on neuromorphic computing, this is a concept in computer engineering referring to the design of processing units that mimic neurobiological architecture present in the nervous system. Neuromorphic computing uses analog, digital, mixed signal, and very large-scale integration systems and software that implement models of neural systems for perception, motor control, or multisensory integration. Last but not least, swarm intelligence is the collective behavior of decentralized self-organized systems, natural or artificial. The concept is a branch of AI addressing the collective behavior of decentralized and self-organized systems comprising of agents interacting locally with one another and with the environment. For Edge computing, different flavors of the concept were implemented as presented in these slides. I will not go into detail. They are very well known: multi-access edge computing, fog computing, cloudlet, and dew computing. Each of them are, in a way, um, different form of implementation of the concept of edge computing. We will focus in the next slide on how the developments in hardware components have accelerated the emergence of edge computing granularity, with the new hardware, software, communication, and AI methods implemented at the micro, deep, and meta edge. These are new forms of edge granularity that implement different forms of edge processing. The micro edge describes local processing to import data into the system. Intelligent sensors, machine vision, and IoT devices generate unprocessed data stream close to the sensors themselves. Further, these devices distill useful information from this data by integrating AI-based elements for inference and self-training. This intelligent micro-edge allows real-time application to become ubiquitous, able to react quickly and intelligently to inferred situation while consuming minimal power. The deep edge comprises intelligent controllers such as PLCs and SCADA modules, networking equipment, gateways, and computing units that aggregate data from multiple sensors. Deep edge devices have a higher power budget since they are shared across multiple endpoints and generally have a more capable processor which can be multiplexed to support those endpoints. If we move to meta edge, this integrates processing units typically located on premises with high performance embedded computing, edge machine vision systems, and edge servers, high performance CPUs, GPUs, FPGAs that are designed to handle computing intensive tasks such as processing, data analytics, AI-based functions, networking, and data storage. Continuum X across the edge granularity combined with the AI approaches as a technology stack that consists of several technologies, including different types of hardware, software, and algorithms. It's an important part of the development of the technologies in order to address this continuum in different applications. This brings new challenges such as addressing the IoT edge functions for distributed and federated learning, integration of heterogeneous computing paradigms, pervasive, edge, swarm, organic into the same application, collective intelligence, and the integration with self-supervised learning, meta-learning, continual and multitask learning, which are new ways of learning technologies that are emerging. The edge nodes are optimized based on the energy, connectivity, size, and cost, and the computing resources are constrained by these parameters. All these elements have to be considered when implementing the Continuum X into the new edge devices. At the same time, IoT edge digital twins modeling, representation, and simulation across the edge granularity and Continuum X brings new challenges. As we are moving towards integrating more and more learning capabilities into the edge devices, AI technologies integrated at different levels of the edge computing continuum requires addressing the learning and inference flow. In this picture, we try to represent the learning flow that starts by collecting the data by the IoT sensor or other type of data collection. Then we have the data preparation, the development of the model based on different AI frameworks, the learning process and optimization of the model with optimization related to computational resources, memory, benchmarking with other type of implementation. Then post-learning optimization, transfer the model to the target hardware and target platforms, and the model deployment of the learning model presented. This brings us to the convergence of technologies that advance the use of swarm intelligence, which addresses some of the challenges faced by the implementation of edge distributed intelligence in the Internet of Autonomous Systems. The swarm intelligence in nature is found in birds, bees, fish, and ants. These creatures have evolved methods of amplifying their intelligence by thinking together in a system. They form colonies and fleets, real-time systems with feedback loops, deeply interconnected, that create new intelligence forms. This emergent intelligence is part of the concept of extrinsic intelligence, with its unique characteristics featuring the creation of brain of brains capabilities. The brain is a system of neurons, as we know, and these neurons are deeply interconnected and create intelligence and intelligent behavior. The swarm, in addition, it's a system of brains that are as well connected, that creates different intelligence forms and behaviors. Swarms are flexible and dynamic, and if we consider, let's say, the honeybees are colonies of different individual bees consisting of a single queen, hundreds of male drones, and probably 20,000 to 80,000 female worker bees. The bees, as we know, are solving complex multivariable problems, providing optimized solutions across the competing constraints using their collective intelligence. How they are doing this? They have a brain that contains about 1 million neurons, while humans have about 100 billion neurons. The honeybees solve complex problems when they think together in a system by forming a swarm intelligence, a brain of brains that combines the knowledge and wisdom and the intuition of the group and converges on optimized decisions. How they can do this? They communicate. They communicate and exchange information, for example, by vibrating their bodies. The vibrations provide signals to the other bees that represent the support for various options under consideration. By combining these signals, the bees engage in the multi-directional exchange of information, pushing and pulling on the decision until they have and they find one solution that they can best agree upon. Swarm intelligence is the nature way, in a way, of aggregating the diverse perspective of a colony or fleet and maximizing collective wisdom. Our interest in the new autonomous IoT devices is how to mimic nature and apply these concepts to fleets of intelligent Internet of Things to enhance the cognitive capabilities of these distributed autonomous swarm systems. There are several key characteristics for swarm systems. One characteristic is the size of the swarm. Swarms may vary from tens to thousands of unit nodes, IoT devices, Internet of Robotic Things, autonomous vehicles, etc. The optimal size of swarm ultimately depends on the swarm's capability and the mission it is assigned to the swarm. Another characteristic is the diversity. In many cases, swarms are described as many exact copies as possible of node units. However, to increase collective intelligence, an autonomous swarm system can mix simple and more complex node units by combining cross-domain node units operating in the air, land, and sea. Another characteristic is collective and collaborative behavior. This requires that the unit nodes exhibit collective behavior involving collaboration among individual node units and the environment. Different forms of communication are needed to achieve collaborative behavior to allow for information exchange among the individual node units. Communication may take various forms and be both explicit and implicit. For example, explicit communication is vulnerable to attacks, spoofing, jamming, hacking, while implicit communication is, for example, encrypted. Is the communication that is understood only by the nodes of a fleet or can be the modeling of behavior of the different members of the same group. Autonomy, decentralization, and distribution are other essential characteristics of autonomous swarm systems, and there are no central units to control the behavior of each individual node unit. Scalability, expandability, resilience, and self-acts functions are as well important parts of the whole swarm intelligence concept. Embedded edge AI solutions for path planning for swarms of mobile autonomous systems are evolving and applied in several optimization and logistics applications. As we can see in this figure, we have different ways in which the swarm can be applied to application in mobility and logistics. What is important that we can use the swarm intelligence in fleet of autonomous devices operating in different industrial sectors and providing optimal solutions for the missions that are assigned to the fleets. The challenges for IoT swarm intelligence are related to aggregation of intrinsic and extrinsic intelligence, the balance between implementing as many as possible decentralized solutions, but at the same time to connect with some form of central unit that coordinates the different applications. Then the local and global sensing and control for the fleets of swarms and how this can be implemented and how the intra-IoT swarm relative sensing, relative locations, collaboration, collision avoidance is integrated into the system deployment. At the same time, another important challenge is how we can apply IoT swarm supervising and federated learning to different applications. The concepts of and implementation of autonomous self-organized edge IoT intelligence system must consider a number of engineering system design characteristics to ensure the dependability and the trustworthiness of the technologies and application for the solutions implemented. These characteristics are, as presented in the slide, reliability, safety, security, resilience, connectability, availability, maintainability. All these together form the concept of IoT and IoRT dependability, which is the basis for building trustworthiness into IoT devices. Few application areas where edge distributed intelligence and Internet of Autonomous Systems are applied in the future are presented in the next slides. In this slide, we are focusing on Internet of Energy, which is an area where distributed intelligence is more and more applied in different applications. We see that in Internet of Energy, the communication, information, energy, and the cost are becoming elements that are exchanged between the different stakeholders in the Internet of Energy application. At the same time, the Internet of Energy concept and the solutions operate at the intersection of several industrial sectors with applications that include mobility, buildings, energy, and requires development of the technologies that are interoperable over the different sectors in which they are operating. Another example that it's very relevant for our discussion is the Internet of Robotic Things. That it's an area where we will see an increase of edge distributed intelligence solutions for implementing new systems, considering the features needed for proper operations, like sense, locate, connect, think, act, and collaborate. These new applications are exactly appropriate for applying the concepts of swarm intelligence with the fleets of Internet of Robotic Things operating in a similar manner like the fleets of swarms as we seen in the previous examples. As we move forward, these features are extended with the need to comprehend and learn that are implemented in Internet of Vehicles applications. The elements of sense, locate, think, connect, collaborate are extended with the functions of comprehending and learning that become essential for the implementation of Internet of Vehicles applications and combining the intrinsic and extrinsic intelligence in this type of applications. As we see in this figure, the vehicle as a part of Internet of Vehicles application can be connected to as much as 12 different communication channels to address the solution and services specific for different domains. As we mentioned that the different nodes in a swarm are communicating with other swarms, as the complexity of the swarm is increasing, as well the channels for communication are increasing. And here it's a clear example of how this will be developed in the future. The new Internet of Vehicles requirements result in evolution of the vehicle's computing architecture And as we see in this figure, we are moving from flat architecture to architecture based on zones. And this allows the implementation of the needed functions in a swarm intelligence fleet that will be implemented for many of the autonomous vehicles in the future. As we see, the complexity of the architecture is increasing, and the functions are clearly defined for the different zones in the zone-based architecture, what brings as well the increase in the computing capability requirements and the use of more complex distributed computing processes and implementations. In this context, these developments will open the way for the implementation of swarm intelligence in Internet of Vehicles application that will utilize efficiently, as I mentioned, the intrinsic and extrinsic decentralized and distributed resources in fleets of vehicles for different applications. And here you have an example of such a possible application in the future. At the end, I will try to summarize and present a number of research priorities that we should consider for the next few years. Few of them are highlighted in this last slide. So the challenges related to addressing the collective intelligence in systems with no centralized control structure requires several new projects and several new implementations. Heterogeneity and diversity of IoT edge requires orchestrators and trustable distributed meta-level operating systems that have to be implemented and adopted. Swarm computing for self-organizing IoT system, physical and virtual IoT edge systems integrated into IoT platforms are another challenge and priority for the future. New ways of programming the intelligent orchestrators using, for example, natural interfaces, voices, drawing schematics, examples, other ways based on AI. It's another research priority for the near future. New IoT and edge computing open, decentralized, and distributed architectures for providing cross-domain resource orchestration in order to implement what we call it the Continuum X integration. It's another priority. Methods for updating and upgrading multiple IoT devices and providing parallel processing capabilities into a distributed system, it's another challenge. Operating system and orchestration mechanisms to address the heterogeneity of these devices, scalability, efficiency, dependability, trustworthiness are, even they are addressed today, are challenges that have to be addressed with further research efforts. Advancements related to processing capabilities, bandwidth, resources, management, and orchestration are as well another area that should get focus in the future. With this, I will thank you very much, and I wish you a wonderful day and enjoy the conference and the rest of the presentation and the exchange of ideas. Thank you very much.